Right, okay, so this is part B of the end of year exam. I'm just going to go through each question and give you some feedback. First question is basically a definition which you need to learn. To get the 2 marks, you needed to talk about the weighted mean mass of an atom. It's important to say atom in this case because it's relative atomic mass. It's not asking you for relative molecular mass. And you had to then compare it to 1/12 of the mass of carbon-12 atom. Okay. Then you were asked to calculate the relative atomic mass of strontium, having been given some information. So you're obviously, when you calculate relative atomic mass, you need to know the percentage abundance and you need to know the mass of the isotope, or the relative mass of the isotope. So we are given 82.9% of strontium-88, 6.9% of strontium-87, and told there's one other isotope. So obviously we replace that with X, and you can work out that there's 10.2% missing. Obviously you add those two up, take them from 100 to get you 10.2, and then it's just really working through the equation, rearranging it for X. Okay, this question tells you that strontium has a high melting point and good electroconductivity, and it asks you to explain the properties, including, and it's quite specific, that you have to include a label diagram, which some of you didn't do. So you lost like 2 or 3 marks, I can't remember, for not including a label diagram. So when you're including a label diagram of something like metallic bonding, you need to show at least 2 layers of the lattice. Strontium has a 2+ charge. It's in group 2. So you need to indicate that, and you need to indicate that there are delocalized electrons. So you do that and you get your 2 or 3 marks. As I say, I'm not sure which. And then you look at each point in turn and explain it. So first of all, look at melting point and explain why it's high. Obviously, because it's got metallic bonds, they're strong. And when you're talking about melting point, you nearly always need to make this statement. So it takes a lot of energy to break the bonds. Obviously, you need to have shown that you know what those bonds are, the attraction between delocalized electrons and the positive ions. Then the second part, why does strontium have good electrical conductivity? Because the delocalized electrons can move. That was really important. You had to show that you understood the delocalized electrons are the charges that are moving, that are carrying the current. Okay, part C. You're asked to write an equation for strontium in water, and you should know that group 2 metals react with water to form hydroxides. Obviously this is group 2, so you have to get your formula correct. OH, 2 lots of OH minus, plus hydrogen gas, of course. And then to describe 2 observations, which would be different if the student had used calcium instead of strontium. So looking at the periodic table, strontium would be more reactive. Hence, calcium, if you use calcium, would be less vigorous. You wouldn't get so much fizzing. The pH would be lower, which this is all stuff that you should have learned. The metal would disappear more slowly, and you would get a precipitate. So any 2 of those 4 would have got you the marks. Okay, part D. You're given some information here about hydrated strontium chloride, and you're given a kind of practical run through, I suppose, and given some data, the mass of the empty crucible, the crucible with the hydrated salt in it, and then a series of masses of the crucible as it's being heated. And then you should notice, obviously, that the last 2, the 3rd and the 4th, are the same, which indicates that all of the water is gone. And then you're asked to calculate the value for X. So you needed to be able to kind of work out which bits of information you needed, and I've tried to highlight that. So you need your relative mass of strontium chloride without the water, okay? And then obviously you had to work out how much strontium chloride, hydrated strontium chloride you started with. So you needed to have your crucible with the salt and take away the mass of the empty crucible, which tells you had 2.69 grams of the hydrated salt. You can then work out the mass of the water, because if you take away, you've got your 18.65, which has got your hydrated salt in it, taken away from the final mass. That tells you how much water was there. Hence, you can work out now the mass of the strontium chloride without the water. Yeah, so your 2.69 grams, which you worked out here, take away the water, gives you 1.62 grams, and then you can work out how many moles, and from that you can work out the ratio. Now, this is unusual because when you're asked for water crystallization, normally you would give a whole number, but this specifically says to give your answer to two significant figures. So some of you did do this calculation correctly, but you wrote 6 down. But so you couldn't get that final mark because you didn't follow the instructions. Okay, so make sure you read instructions in exam questions. Why does the student take 4 readings? Obviously, that was to ensure that there was no water left. And then 2 modifications that would reduce the percentage uncertainty. Okay, so to reduce the percentage uncertainty, if you used a balance with a higher resolution, more decimal places, however you want to say it, and use a larger mass of hydrated strontium chloride, they're really the only 2 things that would reduce the percentage uncertainty. So saying repeat it and that kind of thing is not what they're looking for here. Okay, right, this is a starred question, so it shows that they want you to write your answer in a coherent way to be able to get all 6 marks, and you need to show that you can do the calculation. It says give full details of quantities, apparatus and method. So you need to do all of that to get the 6 marks, and you need to write it in a fluent way. Okay, so initially you can do the calculation to work out what mass of magnesium nitrate you need. A lot of you got confused here, and we're talking about heating the magnesium nitrate to get rid of the water, which you don't need to do. Obviously, if you're making a specific solution, 0.4 moles per dm cubed of magnesium nitrate, the hydrated version, you don't have to drive off the water. So that was kind of like, yeah, you got confused, and you need to maybe do a bit of reading around practicals, and when we do practicals, really focusing on what we're doing, what apparatus we're using, etc. You will get these questions in the final exams, there is no doubt. Okay, so first thing, obviously, to be able to get your 6 marks, you've got to get the calculation correct. So that's there for you. And then you've got to go through the steps, step by step. Okay, so you weigh the crystals, you know, on an accurate balance. You need to indicate that it's got to be 2 decimal places or more. You dissolve the substance in the beaker, transfer to a volumetric flask. If you didn't say volumetric flask, and some of you said conical flask, I think, I don't know, you need to get to know your apparatus. Rinse the beaker, funnel, stirring rod, and transfer it all to the flask. Make up to the mark. Use a drop-in pipette to ensure accuracy at the end, and the bottom of the meniscus should be on the mark, so you need to show that you understand that. And then finally add a stopper and invert several times. So to my mind, most of you've done this practical. If you'd known the steps, learned them, how to make a standard solution, even if you hadn't done the calculation, you would have got a level 2 answer and got maybe up to 4 marks. Okay, so well, here we go again. Okay, so moving on to the second part of the question. Calculate the minimum volume in cubic centimetres of a given concentration of nitric acid that you would need to prepare a solution containing 5 grams of magnesium nitrate. Give your answer to 3 significant figures, okay? And you're given all the information that you need. You've got the equation, you can look at ratios and things. So, work out your moles of magnesium nitrate from the information given, 5 grams. So that's how many moles you need to prepare. Number of moles of nitric acid, the ratio in the equation, you need twice as much nitric acid as you do magnesium nitrate. So you multiply that by 2 and then work out the volume. Pretty straightforward. Don't forget it's asking you for cubic centimetres, and it's also asking you to 3 significant figures. So, to get all the marks, you need to recognise that. Redox reaction here. Know the rules of oxidation, of redox, okay? How do you calculate what's been oxidised, what's been reduced? So the obvious one is oxygen. So that's the first one you should do, because here you've got oxygen as an element, here you've got it in a compound. So it's going from -2 to 0, and then it's just working out whether it's the magnesium or the nitrogen that has been reduced. It's pretty straightforward, to be honest. Okay, as long as you know the rules of working out oxidation numbers. Don't forget, oxidation numbers are per atom. Okay, question 23. This is a mechanism, iodopentane by being hydrolyzed by sodium hydroxide. So this is a substitution. Now you need to show the lone pair on the oxygen. You need to show it coming into the carbon, the positive carbon, delta positive, delta minus. You need to have that on there. Obviously, as the oxygen attaches itself, a covalent bond is formed between the carbon and the oxygen. The covalent bond between the carbon and the iodine must break, because carbon only makes 4 bonds. So there's your product, and you had to include the I minus. If you didn't have that in there, you didn't get the final mark. So you might get the 2 marks for the curly arrows, but if you just wrote this, the alcohol, you didn't get the final mark. You had to put I minus as well. So don't forget, the equation's got to be balanced. Okay, so when you're hydrolyzing when you're hydrolyzing the haloalkanes, obviously what you're doing is looking at the time for the precipitate to appear. So the one that appears fastest, obviously, has the weakest bond. So why does iodopentane react faster than bromopentane? Because the bond is weaker between carbon and iodine than the carbon-bromine bond. Okay, mass spectrum. Okay, so the final peak here gives you the molecular mass, your original molecule. It will give you the molecular mass of that. And then you're asked to write the structural formula for ions that were formed at Y and Z. Now, it's very important that you put the plus charge in. If you didn't, you don't get the mark, because they are molecular ions. They've lost an electron, don't forget. That's how mass spectrum works. So 71 and 43, 71 is 5 carbons, and 43 is 3 carbons plus the hydrogens. You kind of get to know those, but if you don't, it's pretty, it's not difficult to work it out. 3 12s are 36, and then 7 hydrogens would give you 43. Okay, we've got an isomer of 1 iodopentane, and you're asked to draw the structure of it. So hopefully that wasn't too difficult, and I think most people got that right. One similarity and one difference in the mass spectra of these 2 compounds. So the 2-iodo 2-methylbutane will not have a peak at 43. but they will both end up with the same molecular ion, won't they? Because they've got the same formula. So that would be the easy answer for the similarity part of the question. Okay, we've given some information on a reaction zinc with hydrochloric acid, and just asked to calculate the volume that you should produce if you're given these quantities. So you just work out moles and then volume. Okay, so knowing those mole equations, important. Okay, yeah, you're given some information on some apparatus here, you're given some data, and then asked to plot a graph. On the graph paper, plot it and label the x-axis, circle any anomalous results, and draw a best fit smooth curve. So to get those 3 marks, you needed to give the time in seconds, you needed to put a correct linear scale on the x-axis, and you needed to draw that first curve. Smooth curve, yeah, not joining the dots, definitely not. You never join the dots in this kind of graph. And then circle the anomalous result, the one that you didn't include in your smooth curve. And then the second part of the question says that the experiment was repeated with the same mass of zinc, same temperature and pressure, but slightly more concentrated hydrochloric acid. Yeah, so it's going to be slightly faster, but it's going to produce the same amount of gas. So it's going to level off at the same place, but it's going to start to level off sooner. Okay, so slightly faster, level off sooner, and that would be 2 marks if you got that second curve correct. And this is obviously a question about why the reaction is slowing down. You had to mention that it was don't forget, it's the concentration of the acid is decreasing. You have to mention that, and the fact then, because the concentration of the acid is decreasing, you will get fewer collisions per second. So some of you only got 1 mark because you didn't mention the bit about the collisions. It does say in terms of collision theory, so you needed to mention collisions in your answer. Okay, so if you use a catalyst, copper 2 sulfate, how does a catalyst increase the rate of a reaction? And I cannot stress this enough, it doesn't just reduce the activation energy, it provides an alternative route which has a lower activation energy, and as a result of that, more particles will have energy greater than or equal to the activation energy. It's difficult to classify copper sulfate as homogeneous or heterogeneous catalyst in this reaction because we've got a solid and an aqueous solution, and obviously the homogeneous catalyst is the same state as the reactants, and the heterogeneous catalyst is a different state to the reactants, but because the reactants are not the same state, you can't really classify it. Okay. Right. Okay, this is just a kind of synthesis type question. So you're given hexamonine, 3 reactants effectively, and you're asked to draw the products of the reaction of hexamonine with these substances. So this one you're asked for the major product, that's important. So here we are, you're adding hydrogen, this is hydrogenation, so basically you're just getting rid of the double bond and adding hydrogen in, and I think most people got that right. This one, a few people got it wrong because you didn't show the major product. Don't forget, it would be the secondary carbocation, that would be the more stable carbocation, and that would be where your chlorine would attach. So your major product would be that. There would be some with the chlorine on the first carbon, but in general it would be on the second carbon. And then finally adding in the bromine. Obviously the bromine has to add on the 2 carbons where the double bond would have been. It doesn't matter if you wrote it this way around with the bromine here, but you had to show them on the first 2 carbons. Yeah, learn your catalysts. So you need nickel, and reaction 3 is this is an alkene, and this isn't. This is a haloalkane, and that is the test for an alkene, isn't it? What would you observe? You'd see that the bromine was going from orange to colourless. Yeah, so just going back to that. So what I'm saying is, when you want to know if something is an alkene or not, if you add bromine water to it, it goes from orange to colourless. So in this case, that's what would happen, because you're adding the bromine, and it would start out as orange and end up as colourless. Okay, and now this is another starred question. So you've got to give a fluent answer, and to get 6 marks, you need to do everything they ask you. I don't think anybody actually took into account this statement, that the percentage yield of hexagonine is 62.5%. So some of you did do the calculation but missed out that bit. So, you did better in the marks than obviously students who didn't do the calculation at all. But you did have to point that out. So don't forget, look at all the information that's given you. They've given you this information for a reason. You really need to see how you're going to mention it in the answer. It's given you all the densities and the boiling points, etc. Okay, so if you want to get 4.2 grams of hexagonine, then obviously we need to work out how many moles of hexagonine that is. From that, you can see it's 1-to-1 ratio. We can see how many moles of hex and 1 mole we'll need, but because it's a 62.5% yield, you're going to need more than just a 1-to-1 ratio, aren't you? You're going to need more than 0.05 moles. So you need to times it by the factor to times it up. So basically 100 divided by 62.5. So you're multiplying this effectively by 1.6. So you actually need 0.08 moles. And then you can work out the mass of that. Once you know them from the moles, you can work out the mass of hexane 1-ol needed. And then you needed to talk, and again, there was a lot of confusion here as to what the process was, but really they're just asking you to purify a liquid. Yeah. So you needed to use a separating funnel. Some of you are heating all sorts of stuff. I don't know. Anyway, so read through what I've said here, but it's a separating funnel, which you would have an organic and an aqueous layer. The organic layer is on top because you've got the density here. So you know that the organic layer would be on top. But if you weren't sure, and some of you did say this, if you weren't sure, you would add a bit of water to see which one increased, and then you would know which layer to save. So that was a valid point. As long as you recognise it was the organic layer that you needed, that's the one you wanted. Okay, so then you would run into a conical flask after you'd taken off the aqueous layer and add a drying reagent, magnesium sulfate or calcium chloride, to take the water, swirl it around, filter off the drying agent, and then distill. Okay, and to get the 6 points, you need this sort of detail in there, like collect the fraction at 63 degrees. Yeah, and because they've told you that, and they've told you that for a reason. All right, somewhere up here, boiling point is, here we are. Okay, so just check that you're using all the information. Okay, if you used hexane 2-ol instead of hexane 1-ol, would you get as much hexagonine? Well, obviously not, because you would get a mixture of hexagonine and hex2ene. Hexane 2-ol is secondary alcohol. Okay, polymerization. This confused some of you. Draw a section of polyhexagonine containing 2 repeat units. So basically you're joining 2 hexene molecules together. Now you could have drawn out all the carbons. All it is a chain of carbons, but you've shown 2 repeat units by adding the C4H9 here. That's representing all the other carbons. It's just a long chain. So you should have had 12 carbons with all the hydrogens. That's all you needed to do. But some of you did seem to get confused with that. And then finally, what can we do with our waste polyhexamonine? Okay, so we could burn it to produce energy, or we could use it for making plastics or other useful organic compounds. I would suggest making plastics is probably not a good use, not in today's world, but anyway. Okay, that's it.